Okay, we are done with our chapter 4. We're done with, Newton's laws. We've done with momentum. We're done with 2D momentum and this entire chapter about Newton's laws and its applications in every single way. Now, what we're going to do is we're going to start with moments, right? Moments, or in other words, we also call this thing torque, right? So, what is a moment? You're already pretty familiar with it. It's about the turning effect of forces, right? Some forces only help you move in a certain direction, but in special scenarios, forces can also make you turn, right? So when we have forces that make you turn, that's what we call moments, or that's what we call a torque, right? So that's what we're going to study. It's 95% the same as IGCSE. We'll still go over all of it, but the level of difficulty of the questions is much, 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 much higher. Okay. So that's why we need to get the basics absolutely really, really, really strong. Okay, let's start. So, what is a moment? Moment is basically the of product of force and the definition is pretty important because it almost always asks this whenever a question comes up, and perpendicular distance from the pivot. Okay, so that means moment m is equals to force multiplied by the distance, but you've got to make sure that they are both perpendicular. So that means when you use the force in this direction, then distance has to be perpendicular. Okay, so you always got to make sure that if the force is in this direction, then the distance that you're taking, it should always be at a 90-degree angle. Okay, so that's a prerequisite to moments. Okay, in fact, you would say this is basically the same as work done, right? What is the difference between work done and moment? Yes, Aris, what do you think? Any idea what's the difference between work done and moment? Although, don't they have the same formula?
Is moment like about a pivot? That's the only difference. That's
No, not exactly. There's a much greater difference. What do you think? Think about it. Like when you do work on something versus when you turn something, what's different? It is close to a pivot, yes, but it has to do something with the force and distance.
Is it because like in moment the distance is perpendicular distance?
Exactly, yes. In moment, you always have force into distance, and in work done, you also have force into distance, right? It's literally the m inverted, but in work done, force and distance must be parallel, and we'll study that after this chapter, hopefully. And then for moments, they always have to be perpendicular. They have to be perpendicular. That means they should have a 90-degree angle between them. Okay, so that's what that means. So, either force is right. If force is towards the right, then the distance has to be, perpendicular to it. Okay, so make sure you remember that's a really, really important distinction. Okay, for work done, it could be, if force is upwards, then distance is also upwards. If force is at an angle, then distance must also be at an angle. But for moments, if this is the direction of force, then the distance has to be 90-degree. Okay, the distance has to be perpendicular to the force that you're applying. Okay, a really good example is, for example, when you have, for example, you've got a door. Okay, what do you do when you're pushing on a door? Okay, now this is the pivot, this is the hinge at which your door rotates, and this is the handle of the door. Okay, now how do you apply the force? You apply a force perpendicular to the distance of the door, right? This is the distance that you're applying it from. So that's why this distance is actually going to be what? This is going to be perpendicular to the force that you've applied. So this is going to be D, right? So that means moment is equals to force multiplied by the distance. And you've noticed that, they have a 90-degree angle between them. So force is in this direction, then distance is going to be like this. It's going to be exactly like this. Why? The definition was product of force and perpendicular distance from the pivot. From the pivot is all. Every single word in this statement is extremely important. Okay. Now, for example, we know that if m is equals to force into distance, okay, that means two things. That means that if, for example, you keep, for example, if you have, so moment is directly proportional to distance. Okay, now what does that mean? That means if you increase the moment, you are going, oh, sorry, if you increase the distance, you are going to increase the moment. Okay, now what does that really mean? That means, for example, if you apply the same force, if you apply same force to different distance, that means greater distance will produce more torque, will produce more torque. By the way, greater torque means greater acceleration. Okay, greater m. Wait, what? If you apply same force to different, greater distance will produce more torque. Okay, now think about it. You better explain with an example. For example, if you apply a force of, let's say, 10 newtons on the handle of the door versus when you apply 10 newtons force over here, right? Very close to the door hinge, right? So if this is, let's say, 2 meters, if this is 2 meters, and let's say this is, a total of 5 meters, then obviously this is going to generate a greater torque. This is going to generate a greater torque, and this is going to generate weak torque. And you can even try it, if you go to the door, it's very easy to turn the door when you push from the handle. But if you try to turn or apply a force very close to the hinge, it's not going to move at all. Okay, so that's the basic idea. Okay, and we also know that moment is directly proportional to the force, right? So that means, if you apply on the same point over here, let's say, if you apply 10 newton force over here versus if you apply 20 newton force over here, right? If you apply 10 newton force, so the moment is just going to be 10 multiplied by 5. But if you apply a 50 newton force into the same distance, so obviously that's going to generate a much greater torque. This is only going to generate 50, whereas this is going to generate 250. So if you apply greater force, of course the door is going to turn much faster. Okay, sounds good. Okay, so one thing that they don't exactly teach in A levels is, which makes it confusing sometimes, is that greater torque, greater torque, just something that really really makes sense, means a greater angular acceleration. So make sure you keep that in mind. That's always very helpful to keep in mind. Okay, just like, for example, in, regular forces, if you apply greater force, you will get a greater acceleration, right? In the same way, if you apply greater torque, and torque, keep in mind, torque is the product of force into distance, but perpendicular. Okay. And if you apply greater torque, it's going to generate in a greater acceleration, right? If you apply a very large amount of torque on your door, the door is going to turn much faster. But if you apply a very small torque, it might move, but it might move much slowly. Okay, so that's the difference between torque and acceleration. Okay, moving on. I'm sure you've also, seen this nut with a wrench. This is a nut. You can also call it a bolt, whatever. This is a nut, and this is a wrench, or you can also call this a spanner, whatever you want. Okay, now this is a smaller length spanner, whereas this is a larger length spanner. Which spanner is going to make it easy to turn the nut, or open up the nut? What do you think, Abia?
Uh, the longer one?
The longer one. Aris, what about you? What do you think?
The long one.
The long one, absolutely, because that is going to generate a much greater torque. For example, if you apply the same force onto both of them, right? If you apply the same force onto both of them, right? But if you increase the distance, then obviously, because this has, for example, I'll make it even clearer. For example, if I apply a force F over here and I apply force F over here, right? So M1 is equals to force into D1, right? And M2 is equals to force into D2, right? Now think about it. F is the same, whereas D2 is different, right? So that means, Since D2 is much greater than D1, then M2 is much greater than M1. That means this one much easier to turn. Much easier to turn. Okay. Sounds good. Okay. Yes. Any questions so far? No? Okay. All good.
Yeah.
By the way, Hanya, if you have any questions, you can, text me on Google Chat because I don't get a notification from Zoom if you write in the chat. Okay. Okay. So now, what are the conditions for equilibrium, if you remember? Now, what was equilibrium, by the way? Aris, do you remember what equilibrium was? What was equilibrium?
Mm, Is I mean, I don't remember the definition, but it was like a
Hmm.
state in which net force is zero and like
Hmm. Okay. Absolutely. Now, conditions for equilibrium is that the resultant forces, and write that down, resultant force is zero. Now, if you remember, resultant force zero means a lot of things. That means your acceleration must also be zero. That means your speed must be constant. Speed constant. Okay. And that must also mean that, object, it could also mean that it's stationary or stationary or stationary. Or it could also mean that forces are balanced. Forces are balanced. So, resultant for zero could mean a lot of things. Okay. Now, there is another condition for equilibrium as well. Abir, do you know what it is? What is the other
Uh,
condition for?
in a closed system?
No. It's actually analogous to the resultant force. The second condition for equilibrium is that the resultant moment must also be zero. Resultant moment should also equal to zero. Okay. Now, we haven't talked about resultant moment, but we'll get to know what that is in just a second. Okay, it's a pretty simple example. For example, let's say this is like a handle or a bar which is fixed about this point. Okay, so that means it can rotate about this point. So, for example, if I apply a force of 5 Newton on this side and I apply a force of 5 Newton on this side, what do you think is the net force? What is the net force? Yes, Aras. Any idea?
like the forces after after the it's the forces of two objects in like opposite direction, the result, right?
Hmm.
Or like
This is this is in opposite directions, right? So they're pointing
yeah,
towards each other. So what do you think?
so the net force would be zero here because
Right?
like
Net force is zero. It's zero
we can
newtons. Exactly. There's no net force on it, because it's kind of like, you're applying the same amount of force in equal and opposite direction. So there is going to be zero, right? Because if this is plus five and this is minus five, then plus five minus five is zero. What about the net moment? Assuming, what is the net moment? What do you think?
net moment
Le-
would also be zero.
Net moment would also be zero. Okay. For example, this is the distance from pivot 1 meter, and this is also 1 meter.
Oh wait,
What
no, no,
about,
no, no,
what do
I
you
don't
think?
think so. Yes.
No,
Wait,
net
that's not.
moment is not zero.
It's
Think about
not.
it. Would it turn?
Yeah, it would.
It would. Okay. What about you, Bia? What do you think? Would it turn?
No.
It wouldn't. Okay. Now, what I want you to imagine is, imagine that, you're holding, for example, you're holding your pencil and you're trying to balance it on at the center. Now, if you try to balance it at the center, it means that the resultant force and the resultant moment are both zero. Okay. Now, this is in fact going to turn. Now, if this is the pivot, think about it. If you have the pencil balanced right now on your finger and you apply a force on this side, isn't this going to turn the pencil in this direction? Which is going to be what? It's going to be a clockwise turning effect, right? And think about it. If you apply a force in the opposite direction but upwards, isn't this going to turn the pencil like this, right? So that means it's going to turn your entire pencil or your bar or whatever that is in a clockwise direction. You can even try doing it. right? So the net moment is not zero. There is a very positive, there is going to be, in fact, there is going to be a 5 into 1 plus 5 into 1 net moment, which is 10 Newton meter clockwise moment. Clockwise moment. Right? Just like, we added the resultant forces. This is the resultant moment. This is the sum of all of the moments that are acting. And because both of these moments are acting in the same direction, right? So for forces, we had positive force and we had a negative force. But for moments, we've got two directions. For moments, it's either clockwise or it's either anti-clockwise, right? So for torque or moment, torque is either clockwise, it's either clockwise. Oh, in fact, let's make it smart. So torque is either clockwise, okay, or or torque is either anti-clockwise. Okay, so these are the two kinds of torques that exist. It's going to either turn your system in the clockwise direction, or it's either going to turn it in the anti-clockwise direction. So because this is going to turn your pencil in a net clockwise direction, that means it's going to not have a net moment. It's not going to have a net force, but it is going to have a net moment. Okay, now, what about this example? Now, in this example, it's the same thing, but over here, you actually do have a net force because both of the forces are pointing upwards. So this is 10 Newton. But what about the net moment? Now, think about it. If you try to balance your pencil on your finger, okay, and you try to apply the same force on both directions, you see that it's not going to turn, but it's in fact is going to go up. So that means it's actually the net force that is acting and not the net moment, right? If you check it, yes, are you saying something?
No, no.
Okay, so this is 1 meter and this is 1 meter. Now think about it. This force is going to turn your system like this, right? It's going to turn or pivot from this point in this direction, okay? But what about the other side? This force is going to turn the system like this because it's going to turn the pencil in this direction, right? So you have an effect which is going to turn it clockwise, and you have an effect which is going to turn it anti-clockwise. So both of these effects are going to cancel out, which means the net moment is zero. Because if this is clockwise and this is anti-clockwise, what is the clockwise moment? That is 5 into 1. And what is the anti-clockwise moment? That is just 5 into 1 again, which is equal to 0, right? So that means the net moment is 0. Okay. So that's how you are supposed to think about this one. Okay. So be careful about in which direction is something going to make you turn. And we'll do multiple more examples like this. Okay. Now, let's do a good calculation question. Okay. How do you even like calculate a very scary little question about moments, and how do we pick which distances are we supposed to take for calculating moment? Okay. So this is the pivot. Okay, now what the hell is this? Let's make it clear. Okay, now basically what this is, okay, imagine, this is an L-shaped bracket that is screwed to the wall. Okay, so this is the pivot, and this L-shaped bracket is screwed onto the wall. Now, what this is going to do is, forget all of the forces, just think about this little bracket for now. Now, this little bracket is hanging on the wall and it is only screwed about this point, which means think about if you apply a force in this direction, if you push the bracket in this direction, that means this entire bracket is going to shift like this. It's going to turn like this. Okay. But if you apply a force in this direction, if you make it turn like this, that means this entire bracket is going to turn like this. It's going to go backwards. Okay. And if it's kind of like a clock. It's going to go like this, it's going to go like this, it's going to go like this. And if you keep applying a force, that's going to, come back down, and it's going to turn about this pivot. Does the diagram make sense for now? Yes, Riha?
Could you just explain it one more time?
Hmm. Now think about it. For example, let's make another diagram. For example, let's say that this is a for example, this is the pivot, and the pivot has been attached to, let's say, a wooden rod. Okay, that's it. So that means if I apply force in this direction, that means it's going to move like this, right? Just like a pendulum, right? It's just like a swing. Yeah, exactly like a swing. If you apply force like this, it's going to swing like this. If you apply force on the other side, what's going to happen? It's going to swing like this. It's going to go like this. Oh, like this, right? And wherever you apply the force, so it's going to either turn like this, or it's going to either turn in the other direction, depending upon where you apply the force. Okay. Now imagine the same thing, but with an extended L shape. That's it. So that means when you apply a force in this direction, that means it's going to turn about that point like this. Like this. Does that make sense? Yes, Bia. So that's the shape we're
Yes.
talking about. Okay, it's like an L-shaped swing. Okay, or an L-shaped clock hand. Yes, Aris, does the shape make sense?
Okay, yeah, yeah, I understood.
Yes. Okay. Now that's the shape what we're talking about is, and we are applying a force on different parts of this bracket. Okay, this bracket can either turn like this, it can go further and turn like this, it can, go backwards and then turn like this. Okay. Now, what we have to do is we have to calculate the moment due to different forces. Okay, you have to calculate the moment due to different forces. Is a certain force going to make your bracket turn or not? Okay. Now, let's talk about force A. Now, I am applying a force A, 10 newtons. And what is the perpendicular distance from the pivot? That's 2.5, right? So 2.5 into 10 is going to be the moment due to A. So moment is equals to force into distance, perpendicular. So 10 multiplied by 2.5. It's going to be 25. Okay. Now, think about where is the bracket going to turn because of this force. It's going to turn your bracket like this, right? Because, this entire thing is going to move towards the right. It's going to make your bracket turn anti-clockwise. Anti-clockwise, right? So this bracket is going to, go a little bit like this. It's going to turn like this. Okay. Then, what about force B? Now, force B, you've got a 10 Newton force and the distance from the pivot is 5 meters. Okay. Yes, Aris, what do you think? What would be the moment for force B? Moment is equals to force into distance. So yes, force B, 10 into 5. This is 5 meters. Yes, Abhiya, what do you think? What's the moment from force B?
Wait, so how would you like
Hmm.
move it in direction though? Because isn't it pushing downwards and the pivot is just
Okay.
upwards of it?
Okay. Yes, you're right. So you think it won't move?
No, I don't think it would move.
It won't. Absolutely. Now, intuitively, of course, it wouldn't move because you're literally, it's kind of like this is the door. For example, this is the door and this is the pivot. And you are applying a force in this direction, right? It's like you're applying a force outwards of the door. That's not going to move because that's not, the force is not perpendicular to distance, right? That's why you've always got to choose the force which is perpendicular distance. And if this is the distance, the force is not perpendicular, right? They're not perpendicular, right?
They're
Force is
parallel,
in this
right?
direction, they're parallel, right? So that means it's going to be zero. Why? Because force into distance are parallel. Okay, so there's going to be no moment. Okay, what about C? Okay, C is interesting. Now, what do you do for C? Yes, Aviha, what do you think? What do we do for C? In what direction is going to, what is, C going to make us turn?
I think anti-clockwise.
Okay, and like this? Yep, that's right. Because,
Yeah.
if you pull the bracket in this direction, that means it's going to probably turn like this. Okay, you're right. But what would be the moment? What distance do I take? What do I take? Do I take 3 meters or 5 meters or 5 plus 3 meters or what?
Do we um use the Pythagoras theorem to find the
Mm-hmm. Okay. No, we don't need to do that. What do you think, Aris? What do we do? Do we choose 5, 3, 5 plus 3, or is it just 0?
I'm not sure about this.
Think about the definition. Always.
So like 3 into 65.
That's right. Absolutely. Always think about the perpendicular distance from the pivot. Now, if you're ever confused about what distance to take, so imagine this is the line of the force, okay? And this is the pivot. What is the perpendicular distance between the forces? It's this, right? If you're ever confused about what distance to take, just extend the force, okay, and extend the pivot in the same direction, okay, wherever the pivot that is. That means this is going to be your distance, okay? So wherever you're confused, just extend the force and also extend the pivot, right? Just draw another parallel line on the pivot. And the distance between these two lines is your distance which you're going to take. Okay. So that means this is going to be 65 multiplied by 3. And if you can even try it. If this is force in this direction, that means you have to take a distance which is perpendicular. So this is the perpendicular distance, right? It's making a 90-degree angle. And we know that if this is the pivot, this is the perpendicular distance from the pivot. Okay. Sounds good. So this is going to be 65 into 3, whatever that is. And it's going to make you turn clockwise. So 65 into 3 is okay. Clockwise, anti-clockwise. 180, and that's going to be 195 Newton meter. Okay. Now force D. What is going to be the moment due to force D? What is it going to be this time? Yes, Abhiya.
we just times 50 and 5?
Yep, that's right. Moment is equals to 50 times 5, which is 250 Newton meters. Why? Because think about it. This is the force, and where is the pivot in the same direction? It is this. Then, if you want the perpendicular distance from the distance and the force, this is the perpendicular distance between the force and distance, right? So it's going to be 5. Okay. So that's going to be 250 Newton meters. And it's going to make the bracket turn again in this direction. It's going to turn the entire thing like this. Like imagine, you're pulling the bracket from over here. So it's obviously going to turn it like this. Okay, sounds good. So that's going to be 250 Newton meter, also anti-clockwise. Okay. Now, what we're going to do is, now we're going to do a few examples to calculate the net torque. And then from this example, we're going to build the law of the principle of moments. Okay. Now, we're going to have the same example for all of these. We're going to have the same object for all of these examples. So what we do want to do is we want to calculate the net torque on the door. Okay. You have this is the pivot and this is the door with a length of 5 meters, from the pivot. Now, calculate the net torque for this example. So where is it going to turn? It's going to make you turn in this direction, right? Your door is going to turn clockwise. By how much? Clockwise by 25 Newton meter. Okay. So obviously, if there's someone pushing the door like this direction, in this direction, it's going to make it turn clockwise. But what if there's someone on the other side that is trying to push on the opposite direction? So that means the door is going to turn like this. It's going to turn like this. So this is going to generate an anti-clockwise moment of 25 meters, Newton meters, 25 Newton meter, anti-clockwise. Okay. What about this example? Yes, Abhiya. What would be the torque due to this force?
Uh, is it just gonna be 0?
Zero. Why zero though?
Because it's like on the pivot.
Exactly. Whenever it's on the pivot, what is the distance from the pivot to the to the force? It's zero, right?
0.
Right. So that means you always take the distance from the pivot to the force. But if it's, if the distance is zero, it's literally on the pivot, then there's going to be no turning effect since on pivot. And you can even try to it. Try to push your door from the pivot. It's not going to move, if you even bring a crane. Okay. Now, next. What about this one, Ariz? There's one person pushing with a 5 Newton force, and the other person on the other side is pushing with a 20 Newton force. What do you think would happen? What's the net torque? Or what's the total torque?
So could you repeat it?
The question is, there's one person that's pushing from the other side with the force of 5 Newton, and there's another person that's pushing on the pivot at a force of 20 Newtons. What do you think would be the net moment?
Nothing.
Nothing. Absolutely, it's going to be zero again. Since both are on pivot. Since both on pivot. Like, if there's another person on the other side, he's also pushing on the pivot. There's another person on the other side, he or she is also pushing on the pivot. None of you are going to achieve anything. Since both on pivot. Okay. Now, let's make a challenge. For example, let's say that this is, I don't know, let's say that this is Hania. Hania is trying to push the door from over here, and Abiha is trying to push the force from over here. Now you see a different force for both of them. Okay. Now the question is, this is Hania and this is Abiha, and Abiha is going to try to open the door from much further, but Hania is going to try to open the force from much further, closer to the pivot. The question is, which one is going to be successful in making the door turn? Yes, Ariz, we'll leave that to you. What do you think? Who do you think will win? Is the door going to turn clockwise or is it going to turn anti-clockwise?
What is the distance of like the
The total
five
door was 5 meters.
total doors 5 meters? It won't that be equal then? Wait, no,
Sure.
1 second. Give
Check.
me a second.
Think about it. Yes,
Uh,
Abhiya, what do you think?
the 5
Hmm.
newtons
Hmm.
force, like
Okay.
5 newton
Okay.
moment,
So that
moment,
means the door is going to turn
anti-clockwise.
anti-clockwise. Okay. Yes, Abhiya, what do you think?
Yeah, I
Do you think
think
you
the same.
the same? Absolutely. Because now Abhiya is going to generate an anti-clockwise moment of what? It's of 25 Newton meters. Why? Because 5 into 5. Okay. But Hania wants to turn or push in the other direction. It's kind of like a tug of war, right? She wants to make the door turn in the other direction. Now, even though she's applying a much greater force, do you see that she does not generate a lot of moment, right? The clockwise moment is only 10 multiplied by 2, which is equal to 20 Newton meter. 20 Newton meter. So, what would be the net torque? What would be the net torque? The net torque is actually going to be, it's going to be 5 Newton meter, but in which direction? Anti-clockwise. Anti-clockwise. Why? Because the anti-clockwise moment is much greater, right? The force or moment due to Abiha is much greater than the moment due to Hania. Okay. So that's why if you increase the force, if you increase the distance, it has a huge effect because it, allows you to apply a greater turning effect without applying a much greater force. Even though Hani was pushing much stronger, right? She was not able to open the door in her direction because she was much closer to the pivot. Okay. Now, Another very simple example. Now try this one yourself. What is this? So this is A and this is B. Is A going to win in turning the door, or is B going to win? Try this one yourself and also determine what is the net moment and in which direction.
So the total distance is 5 again, yeah?
Yes, again, yes. It's 5 for this entire example.
Okay. It, will it be equal? I mean, like,
Okay.
it wouldn't move because
Hmm.
the moment of B is
Exactly.
through
They're going to be
clockwise
equal.
moment, it is,
They're going to be equal.
and like
Absolutely.
it's 50 anti-clockwise.
So anti-clockwise is going to be, it's going to be 10 multiplied by 5 equal to 50
Yeah,
Newton meter.
yeah.
But to compensate for that larger distance, person B was applying a very great amount of force at a shorter distance, right? So for clockwise, you also had 1 times 50, which is also 50 Newton meter. So that means there is a zero net torque, a zero net torque. Why? Because in this direction, in this case, the clockwise moment, the clockwise moment is equal to the anti-clockwise moment. And when they're equal, that means there is going to be no net torque. Okay. Now, this leads us to the next principle of moments, which I'm sure you've studied it before as well. We call it the principle of moments, where we say that in equilibrium, or in fact, no, wait, how do I define it? So, how you define the principle of moments is that in equilibrium, the sum of clockwise moments is equal to the sum of anti-clockwise moments. That's basically the same thing as saying or you could say, or net moment is equals to zero, right? That's the same thing. So, but this is a more advanced, or you could say a more complete definition, that in an equilibrium, the sum of clockwise moments is equals to the sum of anti-clockwise moments. So that's the basic idea of principle of moments. Okay, now, how do you write this down with an example? For example, this is the pivot. Let's say that, this is a wooden bar. And on that wooden bar, you have multiple shapes of different weights and masses. Okay. Now, think about it. If this is a wooden bar, that means it can either tilt in this direction, it can tilt like this, or it can tilt like this, right? It will depend upon, you know, the distance at which these masses are, and it will depend upon the the different forces, right? Different masses that you have. Now, this object is going to have a weight of weight 1. In fact, let's make it weight B. This is going to have a weight which is equals to weight C, and this object is going to have a weight of W A in this direction. Okay. Now, for example, for example, how would you write the principle of moments in this direction? So, if you are in equilibrium, that means that the sum of clockwise moment should equal to the sum of anti-clockwise moment. Now, what are the anti-clockwise moments? So I think this is going to turn you clockwise, and this is also going to turn you clockwise, right? Because it's going to make your rod tilt in this direction. Now, what is the clockwise moment? In fact, let's just write this over here. It's the same thing, doesn't matter. Okay. Now for clockwise, I see that what is the force of this weight? Oh, sorry, what is the distance of this weight from the pivot? That's going to be WB times D2, right? Plus, what is the other moment that is acting on, that is going to make you turn in a clockwise direction? It is this, right? C is going to make you turn in a clockwise direction as well. But what do I write for the moment? It's going to be the force multiplied by the distance. WC multiplied by D3. No, it's not going to be D3. It's going to be D2 plus D3, right? It's a common mistake that oftentimes they will give you this distance as, 2 meters and this as 3 meters. Oftentimes, what they do is, what students do is that they will multiply this force multiplied by 2. But this 2 meters is only till the next force. That's not the distance till the pivot. You have to take the distance till the pivot, right? So you've got to add up D2 and D3. Okay. So then what about on the left side? What about the anti-clockwise moments? This is going to make your object, your bar it's going to turn in the opposite direction or anti-clockwise, right? And what is the force? That's is WA multiplied by D1. So in equilibrium, this statement should hold true. Okay. Yes. Any questions up to this point? This is all IGCSE stuff up till now. No?
Yeah.
Now what we're going to do is, now we're going to write the principle of moments for A levels. Okay. It's basically the same thing. Oh, let me charge it. In fact, okay, let's take a 10-minute break. Okay. And do come back to this link in 10 minutes and I'll charge up my device by then as well. Okay.
All right.